Well, good afternoon, everybody, and welcome along to the December edition and last edition of Data Platform Downunder for 2021. We've got Thomas Grosser talking to us today about scaling clustered column store indexes. This session is being recorded and will be made available on the YouTube site after the session has finished. Throughout the session, if you've got any questions, feel free to bring yourself off of mute. You can ask Thomas those questions, put your hand up or put them in the chat window and we'll get those questions answered for you. So with that, I'll hand over to Thomas and we'll get today's session running.
Okay, let me share my screen. Button here, button there. Okay, you should be seeing the first slide. So, hello everybody from the other side of the planet. For me, it's still yesterday and late at night, but I hope everybody has a great day so far. And today we're going to talk about how to scale clustered column store. Yeah? So this is not a session about how column store, the basics or so. So this is, you have a column store and you want to make sure it will run as efficient as possible. Yeah? To be in the right window. Here we go. A little bit about me. I'm with SQL Server for 27 years now, maybe already 28 years. It's hard. I started with version 4.21, and I've used every version in between up to the community previews from 2020. For the last 12 years, Microsoft made me an MVP, which helps me to yell at them even more efficiently than normally. Before that, here's my email address and my LinkedIn. If you don't ask a question right here and you get one tomorrow when you go over it again, feel free to email me. I try to answer as quickly as possible. And yeah, so that's about me. So today we have a very short agenda. I will briefly explain how column store works, and then I talk about how to help clustered column store to be more efficient. Yeah, it works. It's one of these many things that Microsoft put into SQL Server that just work. But if you do a little bit more work, it works way better. And that's what this session is about, to show you what, if you follow a couple of extra rules that are not in the big fat top lines of the books online, but they are kind of there, but nicely hidden, you can make column store much more efficient. And then you can ask me as many questions as you want. So how clustered column store works. Yeah. Before we get to that, we quickly have to recap how a regular row store works. You have, for each and every row in your table, you have a little row header, and then following the individual columns after that, they might take up various amounts of space and storage. So on. And then you have the second row, which might be a different length, same length, all of that. Bunch of these rows go onto a page. Page is 8 kilobytes, and then multiple page becomes an extend, and so on. And this is where we are. Whenever SQL Server has to get to any data in a row store, it basically has to pull at least the page that the row is on into memory, sometimes more, and then find the row on the page. This is usually done through the slot array at the end, and then go through the individual columns. Yeah? This is how row store worked, and this is how SQL Server, the only way SQL Server could store data for more than 20 years. Column store goes a different way. In column store, data is stored column by column, not row by row. Yeah? So basically 90 degrees flipped around. Yeah? So SQL Server stores column A for the value for row 1, 2, 3, 4, and as many rows as fit into one of these buckets at a time. They're called row groups. And then second column and all the values, third column, and so on. Yeah? If you need more values than fit in a single row group, then SQL Server will open another row group and put the values in again, keeping up. So the big difference here is that when now you only select column A and C, SQL Server will not even look at the data of column B. It doesn't have to bring it into memory. No there. It will just load the values for A, load the values for C. You can also, by this storage format, already imagine that it's much more efficient if you have to sum up column A if they're all next to each other instead of placed in different rows in different places on the data pages. If they're just one after the other, you might be able to write much more efficient code to do so. Yeah. If you're interested in even more details about that, of course, Bob Ward did a deep dive on how column store internals work. It's on the past summit. By now, I think all this stuff is freely available on the interwebs and can be looked up in YouTube. Thing is, and of course, there's that unbelievable blogs about column store from Nico, and he had written like almost 300 blog posts about column store and every little detail about these things. Yeah. Column store history, let's go over it a little bit so that you understand why you have to work on a more recent version of SQL Server than on older ones. Yeah. In 2012, Microsoft introduced column store. And back then, it had to be on top of a regular table, and it was read-only. So the moment you added the column store, you couldn't insert any new data into the table. Yeah? So it was basically only usable for data warehouses that were loaded once a day, because what you basically every day had to do is drop the column store, add your new data, rebuild the column store. And yeah, it was better than nothing, but I did not know anybody in SQL 2012 that actually used that on a large scale. 2014, column store became clustered column store. Yeah, so the old read-only version still existed. You had a regular table you could put on top of it, or you could convert your table into the column store. Like when you have a heap and you put a clustered index on it, the clustered index becomes the table. And the same is with the clustered column store. Yeah, it becomes the table. There's no other copy of the data. It's only there. And you can do insert, update, deletes. But as we will learn later on in this session, it's a very bad idea to do that. 2016 also made the secondary index. When you put it on top of a regular table, you could also add data there on the fly. You could have filtered secondary indexes where you put like a where clause on the index, so not the whole table is indexed, but only the rows that you match the filter criteria. And you could start building normal B-tree indexes on top of a clustered column store. Yeah. I tried that once in a large scale, and it was kind of funny result. The clustered column store that had a couple of hundred columns took less space on disk than the one index on an 8-byte big int primary key that we tried to add. So after a while, we gave up and stopped doing this because it more than doubled the storage that we need, because the clustered index was not compressed at all. The secondary index was not compressed at all, and therefore took more space than the whole data and things. In 2017, they added computed columns, so a column store now could have computed columns. Yep. And in 2019, it's online create and rebuild. So that was very helpful, so that if you have a multi-billion, if not trillion row table, that you can rebuild that index while everybody's using it. So that's helpful. But for me, before 2016, column store was not really like mature enough to use it anywhere in a large-scale production environment. Yeah. Currently, all my clustered column stores are on SQL 2019. I don't have anything anymore on 16 or 17 or even 14 or older. So that's where I'm right now. Okay. So now to the meat of and the core and most important part of this presentation. The goal is to build a column store, a fact table for kind of a data warehouse application. And believe me, if you have an OLTP system, column store is the wrong idea there, because we'll learn soon why. So goal is to have a gigantic column store with billions and trillions of rows, and how to make it still return query results in a very, very reasonable time really quickly. So the solution, as I said at the very beginning, is the trick is to help column store to be better and more efficient by following a couple of extra rules. The second one is, to be efficient, we need a nice physical database to exist in. And with physical, that has nothing to do if you're running on a VM or running in a physical environment. It just means you have a database that is created. And yes, the second part is we have to insert data so that row groups are created perfectly and super efficient and not half filled and stuff like this. We have to use partitioning with a partitioning key that is actually used in all of our queries, or in almost every one of our queries. We will use and learn how to use data types that column store likes. He likes some, and he tolerates others, but he's not efficient in using the others. So the database. The biggest thing to learn is that under the covers, column store data is stored in regular tables as var binary max. So column store, when they take this one column in one row group, this million rows there in this one row group, they compress it, and then that compressed binary thing they store in a blob, in a var binary max, in a regular table, which at the time seemed like a good idea. Problem is, whoever tried to shrink a database file that has a table with blobs on it will understand why this is not easy to manage. The problem is, once you have a table that has binary large objects, so var binary max, varchar max, text, image, anything like this, the moment you have that, when you shrink your database, or you try to shrink a file, to move a page, they have to do a full scan of the underlying table that the page belongs to. So if you have a terabyte table and you want to move 1,000 pages, which is nothing. Yeah, a terabyte database has millions of pages, but if you just want to move 1,000, you have to read a petabyte of the database. Yeah, so you can imagine this never gonna finish. Yeah, so the big problem is you can practically not shrink data files that contain a column store. Yeah? So my recommendation is to always put the column store in its own file group and in its own files. Yeah. If you need to free the space in the beginning of the file because you dropped some data there, and so it's easier to rebuild the index than to actually try to shrink the file. Yeah. To plan ahead, as I said, put it in your own file group and your own files. I usually like to use 12 or 24 data files depending on the size. This is a personal preference. There's no gain through that. It's just if the data amount that I usually work around with is that we were ending up and having multi-terabyte databases. And if I have like, let's say a 10 terabyte database and I use 12 files, each one of the files is going to be below 1 terabyte, which is a size I'm very comfortable with using these days because any hard drive I will buy or find will fit the data file on it. Yeah? So I don't have to do special constructs to do that. If it gets larger into the hundreds of terabytes, I probably go with 24 or even 48 data files just to spread it out and have flexibility on where to put it. So let's start with inserting data. That's the basic. So we have an empty column store, no data is in there. How do we insert data? And for that, you will meet the first of your two new best friends. This is your best friend, 1,048,576. This is how many rows you have to insert in one go into a column store to make row groups as efficient as possible. Yeah? So why this funny number? It's very simple. It's 1024 times 1024. So it's basically a megabyte, a mega number of rows. Yeah. So the typical computer base 2 counting, it's 1024 times 1024. That's how many rows. Yeah? So a row group consists of up to 1,048,576 rows. And the best practice is, if you want the most efficiency out of your column store, is to insert that many rows at a time. If you insert less than 102,400 rows, sorry. So if you insert less than 102,400 rows, they are stored in a regular row store, delta row group. So what SQL Server creates in the background is then a regular table, puts the rows in there, and then unions the results together every time you query in the background. Yeah? So never ever insert less than 103,000 rows, because that will definitely get you individual rows. And this is one of the biggest reasons why you can't use clustered column stores for OLTP systems, because OLTP systems insert one row at a time. Yeah? Yeah? If you insert more than the 102,400 rows at a time, let's say 500,000 rows, yeah, then an actual row group is created, but not all the available slots in that row group are used. Yeah? That doesn't take up any extra space, but what it prevents SQL Server is from efficient compression. So put it this way, 2 500,000 row groups take up more space than 1 million. Because if duplicate values exist, and there's one copy in this row group and one copy in the second row group, they cannot be compressed with each other. But if they're both in the same row group, they will become compressed with each other. So they like SQL figures it out and stores the value only once. Yeah. So not putting in the full number of rows in a row group will always waste the ability to compress. Yeah. If you insert more than that number, if it's exactly twice as much or 3 times as much or 10 times or any even factor of that, then it's fine. Then SQL Server will create multiple row groups with that many rows. But if it's like 1.5 million, SQL will create one perfect row group and then one with the remaining number of rows. Yeah? If you just insert like 1.1 million or so, then it will create one perfect one and then add the remaining data as a regular table. Yeah? So this is the tricky part. You always have to insert that number at a time. If you don't do it, you can clean it up. So it's not like a mistake that you can never fix. But for that, you have to rebuild the column store index. And believe me, once you reach a couple of billion rows, like 100 billion or so, rebuilding a clustered column store is not fun because it takes a while. So for that, this is the insert architecture I usually try to use. So some process is creating the data. Yeah? This can be something that collects something, some ETL, or individual OLTP systems that write individual rows, or you're subscribing to some message bus like Kafka or so that provides you with data. That's fine. Yeah. That I try to use the bulk insert API because normally the data comes in large batches in places I work, but if it's individual rows, you bulk insert into an in-memory OLTP table, or if you don't want to use in-memory OLTP, a regular table. Put the data somewhere in a traditional storage architecture that does not involve custard column store, and then have a second process that runs as a SQL agent job, or you have your own job scheduling thing, it's fine, that waits for that number of rows, for the 1,048,576 rows, to be in that buffer table, and then reads that one out and batch inserts it in one go into the column store, and then keep on repeating that process. And the big column store then fills up one row group at a time with perfect number of rows in it. So that's the basic architecture. The nice thing is this part is in SQL Server, this part is usually on your app server, and you can have multiple of them using that at the same time. If you have multiple processes that all write into that buffer table, and then one batch that collects it up. Okay. Deleting data. Okay. So data is not deleted in a column store. It's just not. Instead, a row store table is created in the background that contains a copy of every deleted row. It's not the whole row that is copied, but it's basically another table that has the position of all the rows that are deleted. And if you actually then delete data and then query the column store, you have to join that data with the column store every time. So even if you just delete one row, they have to join this one row to everything. If you delete a couple of million or billion rows, you're going to see massive degradation in the performance. Yeah? Column store will just not delete. The only way to fix it is to rebuild the column store once you deleted rows. Yeah? So deleting data in a clustered column store, very bad idea. Performance goes immediately downhill. I think it's, so you can clean up by rebuilding the column store. So just imagine you insert row by row and then you delete every row. You now have to basically read two tables, join, merge, union them together with an empty column store, kind of, to just not get any row back. Yeah, so that's almost like the worst case scenario. You think it can get worse. Updating data. So column store can't update data. So update is implemented as a delete followed by an insert. So if you update a single row, it will create the one table in the background that marks that row as deleted that needs to be joined, and then we'll create a single row insert into column store into a new row group, which most likely is going to be a delta row group that only has one row in it and is a regular table as well. So if you update all your data, you make sure that it's not actually in the clustered column store. Yeah. So avoid updates. If you have to do them, you have to rebuild the column store. So to recap the whole data inserting, updating, and deleting, insert into 1,048,576 rows at a time. Don't update, don't delete. If you have to insert either in a different amount of data, you have to update or delete, plan on very quickly after that rebuilding the column store index. That's the only way you gain back performance. So after going through the whole thing are there any questions? Because I don't see anything on the app.
Not at this stage, Thomas.
Okay, great. So selecting data. Another good/bad news at the same time, column stores only have one access method. It's funny that they're called clustered column store index, while practically the only way to get data out of them is a full table scan. They have no index functionality whatsoever. Yeah? There's no lookup, there's no range scans or anything else. Everything is to be a full table scan. To be very precise, because that makes a big difference, it's a full table scan with partition elimination if the table is partitioned. Yeah? So this column store index, clustered column store indexes need to be partitioned. Yeah? And the partition key needs to be, it needs to be something that narrows down the number of partitions that need to be scanned every time. Yeah. So it's not about a convenient, nice little you might end up with the date to be the partition key, because if each and every one of your queries filters on a specific date or a date range, then that makes total sense. Yeah. But it might be something else. And I think I'll show what we use. Yeah. The goal is that you can really filter on that, and it needs something that is pretty much in every query, because if you don't filter on the partitions, you are scanning all of them. Yeah? And even with all the optimizations they did, that is a lot of work, and we want to avoid it. Yeah. You have to consider the partition limit inside SQL Server. There's a 12,000 or 15,000 by now limit of how many partitions you can have per table. But if you Google the interwebs, you will see that people will tell you, and I'm one of them, once you reach 3,000 to 4,000 partitions, that's the upper limit. Everything above that, SQL Server becomes funny. So let's avoid funny here and stay with about 3,000, maybe 4,000 partitions. Yeah? And for example, if you do daily partitions and you want to save 10 years, you can do 4,000 partitions over 10 years. So it's usually enough. How many you have? Date is usually the easiest to implement, but there's cases where a surrogate key might be more efficient. So what I'm meaning is, you can build your own surrogate key that will limit the data more or give you more granular ability to eliminate partition. Because SQL Server only allows you to have one partition key. So if you have like a group and a date, it's hard to put that into one. So what we came up with is instead of doing daily partitions, which we figured out, since most of the time we want to query a whole month at a time anyway, didn't make any sense. So instead of just storing the date as a partition key, we came up that we took the year, the month, as a 6-digit number, multiplied it by 10,000, and added the ID of the product group, which was a short int. Yeah. So and we knew that we never would have more than like 5,000-6,000 product groups, and practically we had like 50 when we started. So that allowed us to have a filter on the date, the month, date range that we needed most of the time, and a product group which narrowed down the amount of data massively. Yeah? So we had 50. So that means instead of having 30 days, we had basically the month and then 50 groups in that. And we combined this into one key and used just an integer, 4-byte integer, to have that stored in there. Yeah? And you can imagine if you use a big int, you have a bunch of more digits that you can squeeze probably a second group or something in there. Yeah? So that helped a lot. Data types. So which data types? The new second best friend in this thing for column store after the 1,048,576 rows is 8 bytes or 64-bit. Yeah? Every data type that fits in 8 bytes, which is the equivalent of 64 bits, column store loves and is really happy to deal with. Everything that's longer or takes more space, column store can handle, but it's not as efficient as if it's 8 bytes or less. Column store just loves up to 8 bytes. Which ones are this? Big int, small int, tiny int, float, binary 1 to 8, character 1 to 8, national character 1 to 4, small money, date time 2, and time. Yeah? So these are the ones that use 8 bytes or less, and very, very efficient when it comes to processing. And the reason for that is that column store, when processing, uses the vector engine that's in modern CPUs. Vector engines are really wide registers, like 256-bit wide in case what SQL Server uses. So 256-bit register instead of a 32-bit or 64-bit register. And then that register is told, oh, you are not these 256 bits are not one 256-bit value. No, they are four 64-bit values. So when we remember in column store, we had like one row after the other for each column. Yeah? So imagine there's 4 rows in memory right next to each other that are all 4 big ints. So what SQL Server can do is it can read all 4 of these in one of these vector registers and then do a sum operation in one cycle on all 4 of them. The same goes for floating point and so on. Yeah? So this is what makes it so fast. Bob Ward explains it really good in this super deep dive thing is. For here, thing is, try to keep them all at 8 bytes, and that works. When you have them at 8 bytes, what you can do is then use something is called filter pushdown. Yeah? So when you select something from a table where something else is between 7 and 25, yeah? And you want column A or column X and column Y have the filter on column Y. Yeah? In row store, you have to load all data pages from disk into the buffer pool, even all data from columns not used in the query. So even column A, B, C, D, E, F, G, all the way to W are loaded in, but then yes, then you scan through the data that you called in the bottom store and return the column X for all columns where the column Y is between 7 and 25. And then in column store, if Y uses more than 8 bytes, yeah, then what happens is you load column store X and Y columns, which is much more efficient than loading all the columns. And then ignore all the columns where the condition fits not the Y column, so that are smaller than 7 or larger than 25. In column store, if Y uses less or equal to 8 bytes, so for example, is a big int or an int, something like this, what then happens is the storage engine returns all the X values for all the rows that are between 7 and 25. So the storage engine doesn't even return the rows that are not there, match the criteria. So that's called filter pushdown. So instead of loading it into memory and then using it there, it only loads the one into memory that actually are needed. Yeah? So that's a big saving when it comes to getting this data processed. The same works with aggregate pushdown. Yeah? So for example, select sum average from a certain table. Yeah? In row store, you have to again load all the pages, go through all the columns, even the columns that you don't actually need in the query, and calculate the aggregate, and then be happy. In column store, if X uses more than 8 bytes, you just load column X from disk, you ignore all the other columns, and you calculate the aggregate. Yeah? If you run column store and X uses less or equal to 8 bytes, guess what? The storage engine just returns the aggregate for each row group, and then all SQL Server has to do is process the values for the overall result. Yeah? So instead of getting 1,048,576 rows back and have to add them up, the storage engine just returns the sum or the average or the count star or whatever you're looking for based on that. And yes, you can combine filters and aggregate pushdowns, filter pushdown and aggregate pushdown. Yeah, so you can write your query that just sums or averages a certain kind of data, and all the storage engine in the compressed state gives you back the few bytes and then lets the engine calculate the overall result. That's a lot of under the hood work that doesn't have to happen if you stay at or below 8 bytes for the data types. The next one is row group elimination. Same thing. Since all this data is stored in a blob in a regular row, if it's less than 8 bytes wide, what SQL team also does is to keep kind of a min-max value for each row group. So for example, if you have like an ever-increasing key, yeah, for the 1 million rows, for the first one, it's going to be 1 to 1 million. For the next one, 1,000,001, 2 million. So they keep the min-max value for each row group for each column, if it's less or equal to 8 bytes. So when it gets to scanning through these row groups and they quickly look, hey, is the values we're looking for, even if it's even possible to have them here? Yeah. So for example, if we are have a query that says greater than 10 million, in the first 9 row groups, the min-max, if it's an ever-increasing key value, will figure out we don't have to look at them because there's nothing there that could ever fit in there. Yeah? So as the thing is, yeah. So row group contains custom IDs 1, 3, 4, 5, and 6, and row group number 2, 8, 9, 11, and 15. Then the min-max values would be 1 and 6, and 8 and 15. Now, if we execute a query where custom ID is 9, it figures immediately out 9 is larger than 1, so it's a possibility, but it's also larger than 6, so it doesn't fit into the first row group. We can skip that one. We go right into the second one. 8 is smaller than 9. Yeah, it fits, but 15 is also larger than 9, so this is a row group that will have a possibility of having the data, and we process that row group. Yeah? It will then still push down the filter and only return the one row where the ID is 9, but it skipped the processing of the first one and probably each and every other one after that. So that's a very good feature to also reduce the work. Again, columns have to be 8 bytes. Yeah. This also is, if you have large amounts of data that you insert, pre-sort them by the partition key and all the keys you expect row group elimination. So for example, if you have a column with an ever-increasing ID because you use identity or something, if you have an ever-increasing date because you, for example, put your invoice date in here, yeah, if you have an ever-increasing running total, something like this, these are all perfect candidates that you sort your column store data before you put it into the column store. That helps the column store compression. So for example, if you insert the same value 10,000 times, column store internally will store something like this value the next 10,000, yeah, and not have that. But Microsoft also built in more sophisticated ones. Yeah. So for example, if column store realizes, hey, this is an ever increasing value, so it's like 1, 2, 3, 4, 5. Instead of storing the actual values, what SQL will say is, okay, instead of the actual values, we store the difference between them. And if you look at an ever increasing key, 1, 2, 3, 4, the difference between two rows is always 1. And then guess what? We can say again, 10,000 times 1, but this time it's a delta. So if the first value is 17, and then 10,000 times a delta of the same value 1, it's 17, 18, 19 till 10,017. Yeah. So this helps SQL Server a lot. And when scanning through the data, skipping over groups, it's an idea to pre-sort them. Yeah. Going back to the architecture that we had before, going back to the architecture, what we in reality did is we let usually a whole day accumulate in that buffer table, and then pre-sorted the data by our partition key, and then by some additional row that we had a lot of filters on, plus I think one more just to in case we have it. But the third one didn't make much of a difference, so we didn't even search for a fourth one. But for 3 columns, we pre-sorted and then batch inserted the 1,048,576 rows at a time till the whole day was there. Yeah, and yes, we had about 6 to 8 billion rows per day, so it was easily to find nicely grouped together ones that compressed more efficiently through that. So next one is batch mode. Since this presentation was made, now there's also batch mode for row store, which is still a little bit different. Yeah. If our columns in a query are columns that use up to 8 bytes, column store switches to batch mode. That's also thing is, which processes about 900 rows in one go instead of row by row. Yeah. This is what I explained before, that when they are right next to each other, it can use these vectorized statements in the CPU to do this. This eliminates a lot of back and forth between the operators in a query execution plan. Yeah. Because the example is if you don't work in batch mode, it's basically you are the like aggregate function. Yeah. You turn to the select function and say, give me a row. Okay, this is the value. I add it up. Give me a row. This is the value. I add it to the existing one. Give me a row. I added an existing one. This is very inefficient. If you would do this with like manual paper and you walk to your filing closet every time you need one sheet of paper, or when you work your printer and every time you want to print, you put one sheet of paper in the printer, you print it, you wait for the error message and you put in the next one. That's not efficient. Yeah? What batch mode does is it says, here are the next 900 rows, please process them, and then we can all move on. Yeah, and then you ask me for the next 900. And 900 is, I think the actual number right now is 918, but that's an implementation thing. So with every version and with every patch of SQL Server, that number can change. It's about 900 rows. The reason for that is the single instruction multiple data things is that when you take the rows they process 4 columns at a time. And if you take 900 rows with 64 bits of data for each row, plus a couple of bytes of overhead and entry, you end up with 64 kilobytes. And the way column store uncompresses data is into 64 kilobyte blocks. And then they can run through that. And currently that's about 900 rows per batch. Yeah. Just an implementation thing is these little headers at the beginning take up some space, but after that, it's fine. Yeah? No. It's much more efficient, less back and forth between the operators, and really helps. So what about data types above 8 bytes? Column store can process them. You can, I think by now you can even put like an really large data text strings and so in it. Yeah. But all the awesome features, aggregate pushdown, filter pushdown, row group elimination, batch mode, we just discussed, will not be used most likely. So it's going to be just a scan through it, and it's still going to be more efficient than doing it in a row store if you scan a lot of data, and especially if you have very wide tables and you need just one or two columns out of them. Yeah. But it's not going to be as efficient as it could be. What we did to make it more efficient, we considered putting this large data that we could not fit into 8 bytes into a regular table and referencing it from the column store, like star, snowflake schema, reference dimension tables, whatever you want to call it. So things that we, for example, referenced out were computer names, yeah, or IP addresses. This is all stuff that needs more than 8 bytes. And we just put them into lookup tables, had an either an short int or an integer as a lookup value instead. And thing is, for filtering, that's usually good enough because if I look for just one computer name, I can look up that computer name in my reference table and then write the query to pass in that ID, and then it can use all the filter pushdown to only give me rows for that ID. Yeah. So it requires a little bit of work, but again, the goal is to make it as efficient as possible. Archiving data. So column store comes currently with 2 levels of compression, regular and archive compression. Yeah? The latter makes data much smaller, but takes more time to query. Honestly, we run everything in archive compression. We don't do the regular one. We rather have way safe data and space that gives us much more than the little overhead. Yeah, it might be because we have enough CPUs to deal with the decompression, but I rather save on space there. Thing is because once you get into the trillions of rows, if you can save 5 to 10%, that's a bunch of terabytes. Yeah, and yeah, storage costs money. Yeah. So archiving to another system. This is where we got surprised because nobody thought about that. So in one of our column stores, we had a very good compression ratio. We had columns that were about the actual data was about 160 to 170 bytes wide. And column store compressed that to about 4 bytes per row. Yeah. So that's how efficient this thing can be. I mean, the data was very repetitive, but still. So we had this down. So after a while, we collected about 1 terabyte of data per month. And after a year went by, we're like, yeah, we want to put the old data onto a different machine. So we created a linked server, bad idea to begin with, and tried to move the data over. We're like, yeah, it's 1 terabyte, it should be fine. No, it wasn't 1 terabyte. When we selected the data, it got uncompressed into hundreds of terabytes and then sent over the line, which took forever in 3 days. So that was not a good idea. So same problem happened with BCP. When we BCP'd a whole month out, instead of it being 1 terabyte in compressed, it was like 20 terabytes uncompressed. Yeah? And then it got recompressed on the archive side. So I have opened cases with Microsoft asking them for a way to just move the compressed rows but right now there's no official way to do that. Yeah. But it's definitely something you have to plan off if you want to archive into a different machine or even on the same machine in a different database. The data intermittent will be completely decompressed and takes up a lot of space if you copy a lot of data at a time. Backups, that was surprising. So we had this awesome compression into the column store, and 99.9% of the database were the column store, plus a couple of tiny little lookup tables. And we still got, backup compression, made it smaller. Yeah, not as much as on a regular database, but it was still efficient enough. And if you look at it, it makes sense because the underlying regular tables have still a lot of data that can be compressed, the ones where the blob data gets stored. So yeah, turn compression for backups on, it still makes sense. Thing is, yeah. So coming to the end, where are the limits? I don't know yet. I haven't reached any. Yeah. I've inserted about 3 trillion euros into a clustered column store table. And yep, that's a 3 with a lot of zeros. I wish my bank account looked like this. It's on disk, it's about 15 terabytes. As I said, 168 bytes of data and 1 to 32. That's 5.5 bytes per row. Yeah, so 32 times. So the 15 terabytes become 15 times 32, which is a lot, which is about half a petabyte of data. Yeah, when you would store that in a regular table. Yeah? That's a gigantic saving. As I said, it's repetitive data. We pre-sort it. We make everything. We normalize everything that makes sense and is too large, but it is. Okay? So where are the limits? Yeah. All the queries that we run against this are 10 minutes or less. That be optimized for. So what we do usually is count star, sum, average, min, max across the data set. That is handled by aggregate pushdown. Yeah? All our data, if you look at the query plan, it always says aggregate pushdown. Yeah? Where date and one more column, that's the column that we have squeezed into the partition key. That's done through partition elimination. Yeah, we always have that date range, like a month and the product group at a time. Yeah, and B, that's the one we use for row group elimination. Yeah, that's one more criteria that we have every time. So we filter on 3 columns, we aggregate other columns, and another one where we do filter pushdown. There's no more row group elimination going on there because the data is too random. But we do the filter pushdown, so the storage engine only gives us the correct data back. And we group by a bunch of other columns as well. And that's also handled by the aggregate pushdown. The whole thing runs in batch mode. Yeah? And with all this happening, we're basically skimming through half a petabyte of data. We're using almost in each query at least half, if not 2/3 of the columns that are in there. And we can answer these questions in 10 minutes or less. Which hardware do we have? It's a 20-core, no hyperthreading machine that has about less than a terabyte of memory. So I think 768 gigabytes or so. And a bunch of SSDs that make up the 15 terabytes of storage. I think we have about 30 terabytes or so storage that we can use in the box. And that machine costs less than about $45,000. Yeah? So that's not nothing, but it's also for this amount, for half a petabyte of data that's can be queried in 10 minutes. That's a pretty good price. So that concludes the planned part of the presentation, and I'm looking forward to questions. Again, my email address, if you send me something, tg@grosso.com. I'll leave that up so everybody can pencil it down. I will be sending the organizers the slides. You can get them. I know it's recorded, so you can listen to it again, send it to friends. It's all this. So, questions?
So, Thomas, we've got one question from Greg.
Okay.
So you've got that. Oh, hang on. You've got 2. He's got. I hear what you're saying about the number of rows inserted at a time.
Mm-hmm.
Have you tried using compression delay to get around that rather than a separate buffer table?
Wait, I'm trying to not share my screen anymore. Here we go. Here we go. So yes, so all these delayed cleanups and all these things are nice when you have tiny amounts of data. If you insert 6-7 billion rows per day and you do not do it the right way, this little tuple mover, as Bob Ward calls it, that goes into the background and tries to do the compression in a delayed form, never catches up. If you insert a couple of million rows per day, pretty sure it might be able to catch up. Once you reach the billions per day, we just noticed it never got to the cleanup phase. It tried something, but we inserted more rows than it cleaned up on the other end. That is what we noticed in by observing it. It's not documented anywhere that there's a limit or so. Thing is, when we forced it to do a full rebuild and this ran for several hours, then it got cleaned up. But we got much better results by doing the inserts correctly. That is for that.
Okay. Does that answer your question, Greg? Feel free to come off of mute.
Yeah, all good. Yeah, no, I was just wondering what Thomas's thoughts were on that. So yeah, good.
So
the other one I had in the list, while we're at it, is it's interesting that Power BI has a large memory model option where it goes to 8 million rows in a segment. I'm just surprised we haven't seen the equivalent.
Yeah. Well, Microsoft takes its time sometimes to make things good. Hey, database mirroring took till 2017 to finally have the missing mode that they forgot in 2005.
One of the things that you did mention, Thomas, was the issues that you hit with extracting that data. And so it was showing you that the size of the data was X when it was compressed, and that when you started to migrate that, you ran into all sorts of issues with the decompression of that data, and that you do have a case open or request open on how can this be done better. I'm assuming that there is no way for you to easily calculate what it might go to prior to you trying to extract.
Yeah, so the idea that I immediately had is the data, the compressed data is stored in blobs in a table with some metadata. Yeah, and the basic idea that I had is I could read that data and insert it on the other side without ever decompressing it because it's stored by partition. And if I want to move a whole partition, I just take all the metadata with the blobs from that partition and stuff it onto the other machine, and it magically shows up there. Yeah. So I was able to read the metadata out and copy it to the other machine, and with a lot of convincing could even get it into the tables in there. But every time I started the engine, it didn't really start anymore. So I managed to extract the data, I managed to stuff it in on the other side, and then have corrupt data. Yeah. So there's some magic going on somewhere. And again, it's a suggestion for Microsoft to have a way to move a whole partition from a clustered column store to another database on hopefully another machine. But even if it's on the same machine, I can move it there, then move the database over and do the same move on the other side again. With some like variation of a BCP tool that can extract that and insert the metadata correctly on the other side. Yeah, there's a lot of GUIDs in that metadata, so my guess is that some of the GUIDs need to be adjusted for the other side, and I just could not figure out how to do that, and nobody should try that. But it's a suggestion, and it will take some convincing, and maybe in 5 to 10 years, we will have a tool that allows to move that around. But It just something. It still works. You can archive the data and move it to another machine. You just have to plan that. Oh, it gets completely uncompressed, so your network needs to be like have some beef and some bandwidth, and do not calculate with. Oh yeah, the space use tells me it's a terabyte per partition. So yeah, a terabyte's gonna take an hour. No, 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 no. Here go 3 days, which is still good enough. If you archive a whole month and it takes 3 days, that's still a doable amount of time. But yeah, it's just one of the many things. So just to give you an idea, that the column store I described here for this project, we took 6 tries to get there. Yeah, so we this was version 6 of the same project till we finally had it in a way that where everything worked. Yeah, because one thing I omitted here from the presentation is we actually have 2 of these tables with different data. One is very large with trillions of rows, and the other one is small with only like 100 billion rows. And for our data to get out, we have to join the 2. And joining 2 column stores is funny because there's only one way it can happen. Since data by definition is not sorted, SQL will never choose a merge sort join. Since it cannot pick a single row, it will never choose a loop join, so it has to be a hash join. And if you try to hash join 100 billion rows, you need a gigantic TempDB. Because that hash table will spill over. There's not enough memory on the planet to ever make that happen in memory. So we could only join 1 month of data if we tried 2 months of data. So that immediately killed our TempDB, and we had 8 terabyte TempDB. And so that, yeah. So if you have 2 column stores and you need to join them, that's a whole presentation in itself, how to deal with that, because it's not fun. It was not designed to be 2 column stores joined. But it's possible, but it needs some working there. Good.
Does anybody else have any other questions for Thomas before we call it end of the day for this session? Feel free to bring yourself off of mute or type in the chat. While you are, I'd like to take this opportunity to thank Thomas for giving us his time and coming along and presenting today on this session. I'd like to thank everybody for coming along and being part of today, but also being part of the meetup group for the entire year. As we said at the start, this is a final session for 2021. We have already got a session registered for 2022 in January, and that's with a senior product manager, Ree Merritt, formerly Ree Irish, who will be kicking off next year for us. With the festive season coming up, wish you all a Merry Christmas and a Happy New Year. Have a safe festive season. Enjoy, and I look forward to seeing you all in 2022. Where we'll have more sessions for you. Do remember that. Yes, Martin.
Sorry to butt in. Just a quick question for you there. Have we changed? Is the group changed the date of the January meetup?
So yes, Martin. So we did push back from because normally where we're on like the first Tuesday of the month, that would be very, very close to the New Year, and people still being in holiday mode, etc. And the date didn't quite work with Ree. So just for January, we've changed the date as per what's on the meetup. So that it gives people the time to enjoy their festive season, as well as so that Ree was not doing a presentation for us while she was on her break as well.
Yeah, nice one, Warwick. Looks like January the 11th. Yeah, I'll just say while I'm on there, thanks to everyone, like Warwick said. And hopefully next year we can all meet up in person at some stage, if only for drinks. I'll hand it back to you, Warwick. Thanks a lot. And all the best.
Problem. Thank you, Martin. Yes, so everybody have a fantastic Christmas, New Year, stay safe, enjoy, and we look forward to hosting many more sessions like this next year in 2022 and to keep your learnings. As Martin said, hopefully we're able to get some in-person meetings happening, but in the meantime, thank you, and we'll see everybody in 2022.
Yeah. Cheers, Warwick. Cheers, Thomas. Thanks a lot.
Thank you. Happy holidays from me too. And yeah, I really would like to be in person down under someday. I just haven't found a sponsor for the flight yet.
We would love to see you, Thomas. We'd love to see you.
But I'm working on it. I'm working on it. My current company has an office there, so there's a chance.
Cool. All the best to you, mate, anyway. I hope to catch you up in person myself soon. Bye.
Bye.
Thanks, everybody. Bye.